Let's prepare on columns and struts. Columns and struts. So columns, we know it already, which is just the vertical member we used in a building for transferring the compressive force. Okay, so normally columns will be in compression only, and there are some similar types of structures called stanchion and struts. Okay, strut means it is the compressive member specifically used in a roof strut. So it is a steel member. Stanchion means it's a steel column. So it's a vertical compressive member in the building. And beam, it's just a jib of a crane. So in the cranes there will be horizontal beam like thing, so we call that as this jib. And then the beam column, so when this beam column joint comes here, no, so here the column will be transferring both the compressive force and also the bending force will be applying there. Okay, so it takes actually two forces in it. And then slenderness ratio, so this we know already, it's the ratio of the unsupported length to the minimum radius of gyration. So this radius of gyration is nothing but it is root of I by A. So we know that I and A everything. So as the slenderness ratio increases, permissible stress and its critical stress and the load carrying capacity of that structure also decreases. This slenderness ratio has an important role in the columns because with its length increasing, the strength actually decreases. Okay, so the capacity actually decreases, and R will be least along the major axis of the cross section. R is nothing but the radius of gyration. So along the major axis of the cross section it will be least. And then some two important points are given. The tubular section has maximum R, so it is efficient. So always the tubular section is efficient only in case of a columns. Okay, and then the H section is more efficient than the I section in case of the column. So this both points are important. They have asked this in the objective questions. And here there are the values for the slenderness ratio lambda. So based on these values only we categorize the columns. Okay, so if it is less than 32 means it is a short column. Short column means it will fail directly by crushing. Okay, and if it is between 32 to 120 means it is middle column, and if it is greater than 120 means a long column. So when it is a long column it will be failing by buckling. And then PC and PCR values given. PC is nothing but the crushing load and PCR is the critical load. So critical will be at the point where the failure happens. Okay, so when PC is less than PCR it is safe, so it is a stable column. Then they are equal, this column is said to be in neutral equilibrium. When PC is greater than PCR means it is unsafe, so it is a unstable column. And then the Eulers formula. So here the length of the column should be greater than the lateral dimension. So these are the assumptions that are taken for the derivation of this Eulers formula. And then the bending stress should be always greater than the direct stress. And this is suitable for long column only, where the failure occurs by buckling alone. So we saw, no, as the slenderness ratio increases, it is failure happens by buckling, no. So that is only they mentioned here for long column, and this is important. Eulers law is specifically for the long column only. Okay, so here the critical load is denoted as PE for Eulers is equal to pi square by L square into EI. So let us study the different cases that we should take for different joints or supports of the columns. Okay, so the column may be two sides fixed or two side pinned, no. So based on that the value varies, so we'll be studying that now. So these are the cases. So the first diagram represents both ends are pinned support. Okay, so when both ends are pinned, the L has to be taken as L only. So PE formula will be the same, pi square by L square into EA. Okay, the next diagram is both ends are fixed. So fixed means you should take L by 2 as your effective length, that is 0.5 L. Okay, so when you substitute this L by 2 instead of this L, the formula will become as 4 pi square by L square into EA. Okay, so this is for both ends fixed, and for both and one end fixed and one end pinned means it is L by root 2. So when you substitute this L by root 2 here means the answer will be 2 pi square by L square into EA. okay. And then if one end is fixed and the other end is free, means the effective length is 2 times the L, so that the formula will become as pi square by 4L square into EI. So based on this type of the supports present in the column, the values for the critical load differs and the effective length also differs. So they may ask this also in objective questions, and the respective values that change happens in the load also they will be asking. Okay, so this is just an addition point, that is in steel the same cases for columns, no, but in steel if one end is fixed and another end is pinned, means we will be using 0.87 for this value instead of 0.707. So these are some limitations that is given for the Eulers rule. So it is also written as pi square by E square lambda square into E. Therefore it is valid for the slenderness ratio less than 80 only, okay. And then is as E is used here, it is valid up to the proportionality limit only, and the relation between the slenderness ratio and the critical stress is hyperbolic. So the variations between these two will be in a hyperbolic way. And then the Rankine's formula, so this is used for both long and short columns, whereas the Euler's theory, so it is used for only the long columns, okay. So here the formula PR is equal to PE PZ by PE plus PZ. So here PE is the Euler's critical load and PZ is the direct crushing load of that column. So you can substitute directly the values and find the Rankine's load, and here PR is also expressed as FCA by 1 plus alpha lambda square. So here we know FC is the yield stress of that column and A is the area, and alpha is nothing but it's the Rankine's constant specifically used here, and lambda is the slenderness value, okay. So here alpha is expressed as Fy by lambda square E. So it actually varies accordingly with the Fy value of different steel. So what steel you are using in that column, so based on that this Fy value differs, and so the alpha value also differs, okay. So this is valid for all types of columns, and load limitations for slenderness ratio is provided here. So these are the values given in the right hand sides for different type of material. That is for mild steel Fy is 3200. So the Rankine's constant alpha, so sorry they have written here as lambda, so that's not lambda, that's actually alpha, okay. And alpha will be equal to 1 by 7500, and then wrought iron will be equal to 1 by 9000, and cast iron it is 1 by 1600, and for timber it is 1 by 750. So these are the values of alpha, that is the Rankine's constant. So you can directly study that value, or else you can study the Fy value and then calculate accordingly. And then the another topic important in this is core of a cross section, okay. So this core means what is the area in which a direct load to act so as not to cause tension in any part of the cross section, okay. So when the point there is where the load is applied, no, so if it moves somewhat with an eccentricity greater, means the axial load will be turned to moment or some bending will be occurring in that column, okay. So which is the limit, so that the applied load is purely compressive, so it does not cause any tension at all in the any part of the cross section. So that area is only called as the core of the cross section. So it is also named as kernel section, okay. So here I have given a diagram for rectangle and square, so you can consider anything. So inside a red color small diamond shaped drawing is done, no? So that is the core section for this rectangle or square. So the length of that core should be, it should be D by 3 or B by 3. So if it is a square, means both will be same. If it is a rectangle, means it's D by 3 and B by 3. And the eccentricity is D by 6 or B by 6. So this eccentricity is also important here. So this is called as the middle third rule. So that a core is a rhombus whose diagonals are D by 3 and B by 3, okay. And the area of this core will be BD by 18, okay. This E is nothing but it should be less than this limit, that is D by 6 it's given, no. So it should be less than this limit so that it could avoid the tension in any part of the column section, okay. So this is only given as E here. And the next one is the solid circular section. So here the core is D by 4 whereas E is D by 8. So here the core area is 1 by 16 of the circle area. Okay, so this core and E is nothing, you don't confuse both. Core is the total value they'll be giving. Okay, so here it is a circle, so it is easy to understand. That is the total diameter of that core is given, whereas E is half of that. It's like a eccentricity from the center. Okay, the similar thing is only in the previous case also. If you see, the sides of this rhombus is only d by 3, but the length, no, that is this length and this length, no, so it is d by 6. So that only we call it as eccentricity, and the sides of that core area is only given as d by 3. Okay, so here the core area is 1 by 16 of the circle area, and for hollow section it's just d square plus d square by 80, that is E is, and the core is also d square plus d square by 4d. So it is just expressed in that way. So this is called as middle fourth rule, because it's by 4, no, the core is, whereas in the previous we saw it as middle third rule. Thank you, and keep watching for the next lecture on strain energy.